and also giving these opportunities to share some of our work. So this work is about combinatorial optimization for the multi-objective EAs. And because when I've doing some work about using evolutionary algorithms to solve multi-objective optimization problems, and also doing some applications. So for lots of applications, I found lots of problem. Most of the problem I applied are combinatorial problems, for example, in the area of software engineering. So in such a case, when I applied multi-objective EAs to those areas to solve those problems, I find the most of algorithms, the well-established or very modern algorithms are perform very similar. So this makes me to think about for the design of multi-objective EAs for combinatorial optimization problems. So today I would like to talk about some very preliminary observation and the result in this area. Okay. Yes. So basically in this talk, I would like to talk about two things. The first thing is multi-objective EAs. These are observations. We find that multi-objective EAs are stuck in a different area at a time. So that means, for example, for NCGI2, in one execution, multi-objective EAs will stagnate in one area. In the second execution, NCGI2 stagnate in another area. So they are far away to each other. This is the first thing, first observation. And the second thing I would like to talk about is a potential way or to tackle this issue. Probably is not a traditional way. It's called a long-elitist multi-objective EAs. Okay. Also, the one thing I want to say is, if you have any questions, because I think that the talk could be a little bit long. So if you have any questions, please stop me, and it's better for the interaction. Okay, so multi-objective optimization, as you know, is a optimization scenario that there are more than one objective. For example, when we buy a car, we probably care about the performance of the car and also the price of the car. Okay, so in this case, usually there's no single optimal solution. There's no car have the best performance, have the cheapest price. Usually there are trade-off solutions. The solutions are not comparable to each other. So what we call Pareto optimal solution. Okay. So evolutionary algorithms are well suited to multi-objective optimizations. There are two reasons. One is, so when you add in one objective, the simple problem the complexity of the simple problem can become very, very hard, very complex problem. For example, for MST, the minimal spanning tree, for single objective MST is a polynomial time problem, but if you add one objective, the problem becomes NP hard problem. So evolutionary algorithms are very suitable to a hard problem. The second thing is the population-based research in the evolutionary algorithm can approximate the whole part front within one execution, with each solution representing the unique trade-off between the objectives. So in such a case, within one execution, you will find a good approximation of the part front. Okay, and then you provide that to a decision maker, then according to their preference, they will choose their preferred solution. Okay, so this is why the evolutionary algorithms are very popular in the multi-objective optimization. There are three classes of multi-objective EAs. I think the most of the research currently focus on the population update, also called population maintenance or environmental selection. So what they do usually is you have a current population, then use the current population, you generate a new solution. Okay, so then you need to decide which solution you need to preserve, which solution you need to discard. So you form the next generation population. So it's a population update. So according to the way of we updating the population, usually there are Pareto-based multi-objective EAs. So like NSJ2, so which use Pareto dominance as the first criterion to distinguish between solutions. So if solutions are not comparable, then they use the density of the solutions in the crowding degree. Okay, and also we have indicator-based multi-objective EAs, so which convert a set of solutions into an indicator to reflect the quality of the solution set. For example, to reflect the convergence and which use the indicator to reflect the convergence and diversity of the solution set. Okay, and the third one is decomposition-based multi-objective EAs, so which usually use a number of ways to guide the search to convert a multi-objective problems into a multiple or into many single objective problems, and using the weight to decide the direction, so to maintain the diversity of the search of the population of the solutions. Okay, so there are lots of research currently in the EMO area working on this. Either they analyze the pros and the cons of such algorithms, or trying to improve them, and or explore different way or different to implement them. Okay, so they all serve the purpose of finding a good approximation of the part front. And indeed, a lot of work on the continuous problem, for example, DTLZ and the ZDT and WFG. So lots of this work is on continuous problem. Okay. So what we do in this work, our finding in this work is we show multi-objective EAs, whatever population update method they use. So our finding is we show the multi-objective EAs, whatever population update method they use, may easily fail on combinatorial problems. And more specifically, they stagnate in a very different area at a time. So that can be a bit interesting because we have this multi-objective EAs, so population-based randomizer search, and we call this global search algorithm. And also we have this sophisticated diversity maintenance mechanism. And we hope at least the algorithm can help us jump out of the local optimum. Okay, but we find this may not the case. Right, okay. Now, there are questions, what multi-objective EAs we choose, we test. Okay, here we consider three types of algorithms: Pareto-based, indicator-based, and decomposition-based. For the Pareto-based, we consider NSJ2. For indicator-based, SMS, MOEAs, which use hypervolume indicator to guide the search. And for decomposition-based, we consider MOEAD. So the one thing we need to figure out is how we decide they stack, because we want to see when they stack, they are stuck in a very different area. Okay. So the one thing is, okay, so we use unbounded archive to store long-dominated solutions generated so far. Okay, so that means, okay, so if the algorithm generates a solution, a long-dominated solution, okay, then we put in the archive. Okay, so which is unbounded. Okay, to trying to store all the long-dominated solutions generated so far. If the archive doesn't change for a while, so here we set 100 generations, because here the population we use is 100. So that means we'll generate. So after the algorithm generated 10,000 solutions, there is no unique, no new non-dominated solution, non-dominated solutions generated. Then we say the algorithm are stuck. Okay. So what problem we test here? Here we consider two combinatorial problems, the NK landscape problems, which is a popular problem in OR area, and also we consider TSP, which is a well-known problems, which both are two objectives problem. And for the continuous problem here, we consider well-established, commonly used problems. We consider DTLZ and WFT. There is one thing we need to consider here is the distance, because we want to measure the distance between the population, right? So then we need to define the distance in the search space. Okay. So here, the distance between the solution for the NK landscape problem, so which is the binary coding problem. So then we use the Hamming distance. And also for the permutation problem, for the TSP problem, so which actually for TSP, the edge matters, right? So in this case, we only consider the difference between the edges in one solution. So here for this permutation problem. And also for real number problem, we use normal the thing to measure the distance. Okay. Then after we define the solution, the distance between the solutions, then we know we are in a good position to define the distance between the populations. Okay. So here we hope the distance is 0 if two populations are overlapping in the search space, and 1 if they are possible the farthest distance in the space. Okay, so if the solution overlapping, we hope they return the distance is 0, and 1 is a possible farthest distance in the space. So based on this principle, then we defined the distance between the two populations is the average, the minimal distance of one solution in a population to the other population. Okay. And also we use the MDS, so which is multiple dimensional scaling to visually present the solutions, because we hope we can eyeball the solutions. Okay. So MDS actually is a dimensionality reduction technique that trying to map the high dimensional solutions into two-dimensional solutions. Okay, so in order to maintain, to preserve the relative distance between the solutions. For example, if we look at this A1 and A2, there are two solutions, each with the 8 binary variables. Okay, so if we map them into a 2D dimension by using MDS, so A1 and A2, then we can see they're close to each other, okay, because actually they only have a 1 bit difference. Okay, and this is the same for B1 and B2 and C1 and C2. Okay, but for different group, for A and for B, so A1 and for A1 and B1, which have a 4 bit difference, then when we map by using MDS, they will not close to each other. They're far away a bit. Okay, as we can see. So then using this MDS, so we can see how actually close solutions are located roughly. Okay. Right. Okay, so result. Okay, so let's look at the result. The first result is NCJ2 on anchor landscape. Okay, here we execute NCJ2 3 times. Okay, so what we can see here is we're using different color to represent different executions. Okay, so for the least figure, for this figure, we can this is objective solution, objective space. We can see for these 3 different executions, the solutions actually are located a bit similar. Okay, and but if we look at the solutions in the decision space by using by using this multi scaling technique, multi-scaling technique. So we can see actually they are from away to each other. Okay, so one execution, so it's a red solutions. They are in this cluster, and for the blue one in that cluster, and for the black one from away to other 2 populations. Okay, so this is the result of on the NK landscape. Okay. And if we see other algorithms, for example, SMS and MOEAD, will have very similar pattern. And we can say in the objective space, solutions are similar, but in the decision space, solutions are from away, populations are from away to each other. Okay, within the 3 executions. Okay, so this is the result on the NK landscape. Okay. So how about TSP? So TSP is another problem with computation and coding. So we can see in the objective space, the solutions are very close, are very similar for the TSP. But in the decision space, they actually form 3 clusters. Okay. And we can see how the very similar pattern as the NK landscape. Okay. So then, the previously we consider combinatorial problems. Now we can maybe consider the continuous problem. For example, we can consider DTLZ1, which are 2 objective DTLZ1, and also WFG. And for those 2 problems, we can see that in the objective space, they are overlapping, and also in the decision space, they are overlapping as well. Okay. For example, for the WFG, okay, so in the decision space, we can see there are kind of 2 clusters. Okay, but each cluster have the solution from each execution. Okay, so then this is the visualization. This is the result, the visualized by the visualization tool. So then if we see the distance, okay, the metric, because we define the distance metric, and here we can see this is the average result and under 10 executions, and we can see the NK landscape here is the 0.4 something, is over 0.4, and for TSP is over 0.7 actually, so very close to the 0.8. So note that actually we do the normalization, right? So that means 0 means 2 populations are overlapping, completely overlapping, and 1 means the solution set are the farthest the solution set. Okay, so the 0.5 or 0.4, 0.7 actually they are very, very far away actually in decision space. But on the other hand, if we look at DTLZ or WFG, so this distance is very, very small, you can see, and it's 0.002 something. So we can see the solution actually obtained by the different algorithms, by different executions the same algorithm is very, very close in the decision space for the continuous problem. Okay, so then previously we fixed the parameters. So we consider a set of parameters. We consider the problem size n is 50. The number of objectives is 2, and the level of the ruggedness for the NK landscape is 10. So it's a bit very rugged, the problem. Okay, so then one may wonder how the different parameters affect the result. So if we change the population size, if we change the problem size, we change the number of objectives, or change the level of the ruggedness of the problem. Okay. So this is the parameter analysis result. So if we change the problem size from 20 to 200, so the number of the variables, basically, so we can see the result won't change very much. Okay, they all have this very similar result around 0.5. So if we change the number of objectives, we can say again they won't change very much. The distance between the solution between the populations won't change very much. But if we change the level of the ruggedness, then the distance changes dramatically. So if the ruggedness level is 2, if k is 2, so which means it's very smooth in the search space, then we can say actually the final population of each algorithm converge into the same area or very close area. But if we increase the level of ruggedness, then we can say when it's a 5, then the distance increased. And when they reached a threshold like 8, then the distance is very, very similar. Okay. Now we have seen our result. So there are some observation I want to make here. So the one thing is the behavior of the so-called global search algorithm, multi-objective EAs. The multi-objective EAs is a global search algorithm. We can see actually the behavior of them can be very local, particularly on the combinatorial problems. Each time they stagnate in a very different area. Okay. And this may indicate the less high effectiveness of the population of data methods in the multi-objective EAs. Okay. So actually we have shown some results. So for example, for the left hand figure, there's this cross, the black cross is the Pareto front. Okay, so it's a true Pareto optimal point for the NK landscape problem. Okay, and then for the different color circles, they represent different algorithms when they stagnate. For example, if we can see NCJ2, so here, and there is a blue one, SMS is, NCJ2 is green, SMS is blue, MOED is red, and all actually when they stagnate, they actually is not close to the part front. They do have some, distance, have a gap to a part front, and we can see here when they stagnate. And this is a maximization problem, and also for the TSP problem. So here is which is a two objective minimization problem, and we can see when the solution end up with actually have some distance to the part front, and also the coverage is not the diversity is not very good, okay, compared to the part front, particularly the spread of the solution. Okay. Another thing I want to just say is most work in the multi-objective EAs currently is on the well-known continuous problems, ZGT, DTLZ, WFG, but sometimes I probably is desirable to investigate or design the multi-objective EAs for combinatorial problems. And another point I want to make is much effort now on combinatorial problem is to develop hybrid search. So, or mimetic search basically is using a local search and multi-heuristic or IEAs, and then use the local search, the powerful local behavior, and to find the good solution in the neighborhood, and also use the multi-objective EAs, the global behavior. But we find that multi-objective EAs, actually the behavior is not that global. Actually, it's a local behavior, a bit local. So this can be detrimental to the hybrid search. Both type of algorithm with the local search, local behavior, maybe not very good. Okay, so this is the first thing I want to talk about in this talk. Okay, so the second thing I want to talk about is, as we say, actually the multiple EAs currently, whatever the population update method they use, they kind of stagnate in the local optimal very quickly. So then, is there any way to think about or to design a different way to consider multi-objective design of multi-objective EAs? Okay, so in this work we kind of use a different way to different route to tackle multi-objective problem, not only a combinatorial problem but also applying to a continuous problem. So which is the non-elitist multi-objective EAs. And I think elitism, which basically for the EA is that will always preserve the best solution from the current solution, current population and the new generated solutions, and we combine, we find the best solution from them, and always we preserve in the next generation population. Okay, so this have been seen a very a default setting for the most multi-objective EAs and also for the EAs. Okay, right. Then, but actually, elitism, which is believed to the major contributing fact that leads to a success of multi-objective EAs. Okay, and we have seen lots of work about using the elitism always preserve the best solutions in the next population. Okay. Indeed, for example, in a recent interview with Sigavo, the DEP had attributed the popularity of NCA2 largely to the use of elitism. And also since the introduction of elitism in the EMO in 1999, almost all the multi-objective EAs use it. And having or not having elitism now is the dividing line between the first generation multi-objective EAs and the second generation EAs. Okay, so then the elitism we can say actually is very, very popular and default setting in the multi-objective EAs. Okay. But on the other hand, interestingly, over the last decade, in a single objective optimization, the long-elitist EAs show they are promising. Okay, by some theoretical research, theoretical study, and they find theoretically, so long-elitist EAs can be better to solve some kind of problems. Okay, so given this a bit contradictory observation, so the motivation of our work is we're trying to explore the possibility of applying the concept of the elitism to multi-objective optimization, and to say, at least empirically, if there is a chance to develop a long-elitist multi-objective EAs that is able to compete with elitist multi-objective EAs. Okay, so this is our motivation. So what we do, okay, so and as we know, for the multi-objective EAs or for the EA, there are very, very simple the framework. Okay, so first we do initialization, and then we use current population generate new solutions. Then we use the current population and the new generated solutions to form the next population, and we'll do this iteratively many times, and hopefully we find very best solution of the problem for the problem. Okay. So then for the long entities, what we do usually is we keep all the same for the step 1, except for all the steps except for step 4. So here for the population updates, we don't change, we don't use the best solution of the current population and the new generation solutions to form the next population. We directly replace the current population with new generation solutions. Okay, so that means we discard the old population completely. Okay, we won't use any good solutions in the next generation. Okay, so here we call this simple, the long entities, the multi-objective EA. So this is a very first preliminary attempt. So we call this simple. By simple, we mean here we don't use crossover. So this actually the production, the process. So here the production process is to produce solutions, right? By using here we only use mutation. We don't use crossover. Okay, so one thing. And the second thing is we don't use any diversity related mechanism, because here we directly use the QT to replace P T plus 1. So here the selection pressure comes from reproduction here. Okay. So for reproduction here, what we do, we use tolerant selection, so which is a very common selection method. And then what we do, we dominant sorting the solutions. We divide the solutions into different layers, which is just like SJ2. Okay, and then we only use these layers. Okay, when we compare solutions. So if the solution in the first layer, then it's better than in the second layer. Okay, so if the solution in the same layer, then we randomly generate one solution to do the mutation. Okay, so you can see the algorithm is actually very, very simple without any diversity related mechanism, and only use mutation. Okay, so what's the result? So here we consider knapsack problem with 100 items. So here the problem is very simple, only 100 items. And we can see here there are SGI2 result and also the result from the long unitist algorithm. We use red color to represent SGI2, blue to represent our algorithm. Okay. So for each algorithm, there are two things. The one is population, 2 items. One is population, one is archive. The reason we use archive is because for the long unitist algorithm, we directly discard the old population. So we need to use the archive to store the best solution we found. Okay, those archives won't evolve in to generate new solutions. They just as archive to external archive to store the best solution found. Okay, so now we can say for the long unitist, it's a circle is actually the archive, and this the point represents the final population. You can see for population, there are lots of very poor solutions in the final population, but the archive only store the best solutions ever generated. Okay. But for the SGI2, there's no much difference because they use unitism, always trying to preserve the best solutions. Okay, into the next population. So, and you can see they are overlapping. Basically, And now we can, if we compare the results between the SGA2 and the long-elitist algorithm, we find that they're overlapping in the middle of the part front. Okay, but for the boundary, there are some boundary assertions which can only be found by the long-elitist algorithm rather than by the SGA2. Okay, so this is the result on the landscape. The knapsack with 100 items, which is the linear problem and a simple problem. Okay, so if we consider anti-landscape, which actually is a very complicated problem with a very rugged landscape, if we set k is 10, then we can see the advantage of the long-elitist algorithms become large. And we can see there is the result, the red one obtained by SGA2, this is the maximization problem. But for the anchor landscape, we can see the final population, the solutions actually are better than what find by SGA2. Okay. So if we, so they are the hypervolume result on the knapsack and anchor landscape with different instances. Okay. So we can say for the KP problem, for the knapsack problem, when the scale, the problem size is small, the algorithms perform very similar. But if we increase the difficulty of the problem, the size of the problem, and also for the anchor landscape problem, we can see the long-elitist algorithm performs better. Okay, so in the last experiment, we compare the long-elitist with SGA2. So how about other algorithms like SMS, MOA, and SGA3? Okay, and they have the same observation. We have the same observation that for the simple problems, they perform similar, and when we increase the complexity of the problem, the long-elitist algorithm performs better. Okay, so let's compare with SMS and SJ3. Okay, so then the question is, how about the continuous problem? And previously we only consider the combinatorial ones. Now how about the continuous? Right. Okay, so the first we consider a very simple continuous problem, ZGT1. So now we can see here the both algorithm, if we know, I think that the part front of ZGT1 actually is exactly this line. So if we know, now we can see that the hypervolume of SGA2 is better than the hypervolume of non-elitist algorithm. Both algorithms actually can find the part front. Okay, so they are very well, but the SGA2 is better. Okay, they can find more solutions, more Pareto optimal solutions. Okay, but if we consider a more challenging problem like UF1, so now we can say actually here the long-elitist algorithm can find the part front, but SGA2 cannot. Okay, so now we can say for the simple problem, elitist algorithm better, but for the hard problem, probably the long-elitist algorithm is more competitive. Okay, so the budget. That is the problem of the long-elitist algorithm is the big budget. You may notice here, actually, the population size we use is 10,000. And the number of generations is 5,000. Actually, it's a very, very big budget. Okay. So then we can say with that huge budget, we can see long-elitist algorithm performs better than elitist algorithm than SGA2. So without the same setting. Then one may ask, how about a random search? Okay, so for example, you randomly generate the same number of solutions, Then you use archive to store the best solutions, that is non-dominated solutions. So how about the random search performs in this case? Okay. So now here we report the result obtained by random search compared with the long linked. We can see for the bi-objective knapsack problem, so this red cross is a solution obtained by random search. And this one is for the NK landscape. And we can see actually those solutions performed worse, much worse than the non-latest. Actually, they perform worse than the latest as well. Okay. Then now we can see some promising, I think, for the long latest, but also there are some limitations. The first one is I already mentioned that we have large population size and many generations. Okay, that's the one thing we need to solve. And the second thing is it's very sensitive to variation rate. Okay, that is here the mutation rate for the long lattice algorithm need to set to be below a threshold, which is log k over k. So the k is here is a tolerant size, selection size, and n is the problem size. Actually, it's very sensitive. It's very sensitive to that. You be slightly below to that threshold. Okay, this is for the non-elitist. For elitist algorithm, they can relatively flexible, so they can set like 0.1 or 0.01, so they can maybe have not much difference for some problems. Okay, and also another thing is archive need, because for the long-elitist algorithm, the next generation cannot represent the best solutions they generated. Okay, so in this case, we need to use the archive to store the very best solutions, that is non-dominant solutions generated during the search. Okay, so it's the three limitations currently of the long-interest algorithm. So based on these limitations, what there are some we want to do is the one thing is we need to develop more effective the long-interest multi-object EAs. For example, we can add crossover in the long-interest framework in the mating selection, and we can also consider diversity-related selection criteria. Okay, for example, use the clouding distance in the tolerant selection. Okay, that's the one thing. And the second thing is we need to reduce the population size and number of generations, because sometimes we don't want that huge budget, right? So a potential way to solve that is to use the selection operator with more selective pressure, for example, power law selection, so which can provide the higher selection pressure toward part front. Okay. The last thing I think we need to think about is theoretical study for the long and latest multi-object EAs. So currently, the theoretical study for the long latest is for the single objective optimization problem. So if we want to understand better for the multi-objective scenario, then we need to consider theoretical study to analyze them. For what kind of problem is more suitable for the long latest? Okay, and finally, let's take away. And the first thing is we can see for this multi-objective latest multi-objective EAs. Okay, so for the population update, so what we do is we always choose the very best solution when trying to form the next population, right? We always combine, or we choose the best from the current population and the new generated solutions. Okay, and then we rank them, and we choose the population size best solutions into next population. This is very greedy and deterministic population update manner, probably not very useful for some problems, particularly for problem with a very rugged landscape, as we can see in the combinatorial problem. On the other hand, so the randomness in the population update of the multi-objective EAs seems beneficial, as we see in this non-elitist multi-objective EAs. So here, this is very random. We just randomly generate some solution and put as a next population, and we can see for some problem they perform very good. Okay, so actually recently, working with Cao Qian's group in Nanjing, theoretically we prove that using this stochastic population update can exponentially decrease the expected running time for multi-objective problems. Here we consider SMS as a SMS MOA as an algorithm, and also we tested them on some problems, artificial problems. We introduce some randomness in the population update can exponentially help the search find the best solution. Okay, so this again is a very preliminary theoretical research, and also we try to test the different problems, and also to consider to analyze other algorithms as well. Okay, that's all for my talk. Thank you.